Frictional Lab by Jacob Shaner, Kirsten Walsworth, and David Wojciechowski. So, introduction. Our research question for the lab is when applying a constant force, how do different surfaces that provide varying amounts of friction influence the kinetic energy of an object being dragged across it? From this, we hypothesize that there will be less work done on the IO lab when pulled across surfaces with more friction. Our results were consistent with our hypothesis. We showed that through our experimental results and using the two work equations that relate to force and energy, we use this as our point. Models. The work energy theorem, which states that work done by the net force acting on a system over a certain displacement is equal to the change in kinetic energy in the system. We use this theorem to relate energy and force of our system and provide stronger evidence for our claim. Frictional forces are resistive forces in our experiment. We know resistive forces act in the direction of opposing motion. We demonstrate this knowledge in our free diagram. The force of gravity causes the ILAB to move to the right, so our vector for frictional forces will go to the left. Kinetic energy is the energy in motion and is dependent on the mass and velocity. The velocity changes from the start to the end of our trial, so we have a change in kinetic energy. System schema and free body diagram will be discussed in the next slide. And net force is equal to the mass times acceleration due to Newton's second law. The next force is calculated later in our experiment. The acceleration and net force are assumed to be constant throughout each trial due to the fact that the force due to gravity acts upon the weights, which we know to be constant at 9.8 meters per second squared. So system schema and force diagram. Our system schema helps us to know the forces that are acting upon the system and what our system includes. For example, our system includes the ILAB only, therefore everything outside of the system is providing work. Free body diagram represents all the forces acting on the ILAB. We see that normal force and force due to gravity equal and opposite, so they cancel. We notice the contact force from the weights are not equal to the frictional force, causing the net force to be greater than zero. Here are a couple of the equations that we'll be using later to make our calculations. And experimental design. The ILAB was laid upside down so that the flat surface for frictional forces to be acted upon. The arrow here is that the gap in the surface of the ILAB due to where the USB attachment goes. Trackers used to determine velocities and the time it takes the ILAB to travel a certain distance. The camera moves very slowly while recording, which could add to some error. The surfaces we decided to use will include the glass tables, wool, and silk. In order to create a constant force pulling the ILAB, we set up a pulley system with a mass hanging off the table. By allowing it to fall, we assume a constant acceleration due to gravity, therefore a constant force of 0.981 newtons. Results. Here are the results that we took directly from Tracker, and we used these to calculate work in the next slides. So the Baer table. Change in kinetic energy was calculated by taking the final kinetic energy minus the initial kinetic energy. Since the ILAB had an initial velocity of 0 meters per second, we can conclude that the initial kinetic energy is 0 joules. Using the kinetic energy equation mentioned before, we found the final kinetic energy, and since the initial kinetic energy is 0, then the change in kinetic energy equals the final kinetic energy. By using known models, we know that the change of Ke equals work, therefore the amount of work applied to the ILAB equals 0.0695 joules. In order to confirm our results, we calculated work by using Fnet times the change in position of the ILAB due to the work thermal energy theorem. Fnet was calculated by using the kinematic equation previously discussed to find acceleration and multiplying the acceleration by its mass. When multiplied the Fnet by the distance traveled to get work as expected, the Baer table, the two work equations produced the same result. So, by using the same method as above to get the calculations, we found work to be 0.0120 joules by using the work equals change in kinetic energy equation, and 0.0115 joules by using the Fnet times change in position. We concluded that although these are slightly different, they're close enough to confirm each other. Wool was using the same calculations as the other two, and we found that the work is 0.0072 joules by the change in kinetic energy equation and 0.0713 by using the Fnet times delta x equation. Again, they are close enough to confirm each other. So discussion, overall we concluded that there is an inverse relationship between the frictional forces acting on an object and its kinetic energy. Through our experiment and calculations, we discovered that surfaces that apply larger frictional forces to the ILAB results in the ILAB having a lower change in kinetic energy. Overall, the ILAB experienced the greatest change in kinetic energy while being dragged across the Baer table, which can be contributed to the fact that the table provided the least resistance. The silk shear provided slightly more resistance than just the Baer table, likely due to the fact that the ILAB was being dragged across two layers of fabric that made up a single shear. It makes sense that the change in kinetic energy of the ILAB for these trials was only slightly lower than the Baer table, as that silk is a smooth fabric that doesn't provide a lot of friction. Additionally, it should be noted that the surface likely had the most area out of the ones tested because it had pockets on the other side and plating down the middle that influenced the motion of the ILAB, which could have influenced our data. Finally, the wool sweater provided the most friction, thus causing the ILAB to experience its lowest change in kinetic energy. Work done in the system is equivalent to its change in kinetic energy, so as the ILAB moved across the wool sweater, the least amount of work was applied. This makes sense because the strong frictional force exerted by the wool resists the ILAB's ability to gain acceleration, which translates to a lower kinetic energy compared to the other fabrics over this change of position. Meaning a lower change of velocity equals to a less work being done on the object. In conclusion, our data does support our hypothesis that surfaces with more friction will apply less work.